That's a great introduction. Welcome, everyone. Thanks for being here. Victoria, unfortunately, could not be with us today, so I will both be the welcome address, which will be very short, and the master of ceremonies. I think we'll maybe keep it more informal than usual. So we have 6 presentations today from 4 speakers. I'm doing the math correct. Many of them on a diverse range of transportation topics, as you'd expect from UC-ITS. I think this is like one of the best ideas we have since Victoria's gotten here, which is to make you all do these posters or slide presentations in December rather than 2 or 3 days before you get to TRB. Get some feedback from a broad audience. Yeah, I mean, I still want to do my presentations when I get to the conference, but maybe I think sessions like this as well. So it says 10 minutes for each of the speakers, and then 5 minutes of Q&A. So we'll try to keep to that. If there's any clarifying questions that you have during the 10 minutes, you can feel free to ask them, but keep your kind of broader discussion questions till the end. It's a little hard to see, which is the downside of this. Yeah.
In that screen, it's a bit clearer because there's no. Okay. I know we can
Can you like zoom, Jared, as we move through?
Yeah, I think you can do that on the
computer.
See, there should be a magnifying.
You can read it though. Can you read it from back there?
I think it's fine.
Okay, this time seems okay. Yeah. Maybe not these.
Yeah. So.
Chenyu, I'll welcome you up to be our first presentation. Chenyu Yuan, a 3rd-year PhD student.
Yeah.
Working with Professor Matthew Dean. And well, he can give you his title. What do you hear what you have to say?
Yeah, hi everyone.
We'll welcome you with the
So hi everyone. This is my first TRB paper, and the title is Plugging to Behavior from Rule to Racing Shaping EV Charging under Synthetic Trip Train and TOU Pricing. So the big background here is that there are growing interest of the transportation modelers to integrate the EV charging activities into multiple activity-based models such as Polaris and also ASM and other platforms. So most of them in the paper, they assume a fixed SOC threshold or always charge if there's available logic. Means that most of the frameworks, they are using the rule-based logic to do this kind of simulation. But most of the survey-based research shows that EV charging decisions are strongly related to the behavior heterogeneity. So here comes the research gap of my research is that how do the behavior modeling assumptions systematically distort simulated EV charging demand under the identical infrastructure and pricing conditions? So it's very important to understand this, because if we want to do accurate demand forecast, or if you want to have more realistic station utilization, or finally, we want to evaluate the policy effectiveness. So that will be very important to test what is stored and what happened if we use different kinds of models. So the contribution of my research is that I used a very uniform behavior experiment into Polaris and shows that simple rules systematically overstate the infrastructure stress, and also how heterogeneous models will reshape the temporal and spatial load patterns. So I do my case study in Polaris and in a small city in Bloomington, Illinois, with 141,000 agents generating over 3,700 daily trips, and the infrastructure setting looks like this in the map. that we have about more than 10 charging stations. And the biggest station is over here at the downtown Bloomington, Illinois, is number 3. And it is also the most busy station. And the TOU pricing is over here that we can see from the very early of the day, we have the off peak, which is $0.3 and come to mid peak of during the day and off peak after 5 p.m. So it's about $0.6 during the day. I use 5 different I use these different models. So the general information of it is shown on this table here. So the most simple one is rule-based model that is just threshold, depends on whether the SOC is under 20%, something like that. And it also consider distance, means that only find the nearest one for charging. And here comes other kinds of logic model I use, such as mixed logic and latent class. So mixed logic means that we only consider SOC, consider price, consider distance, and we find the maximum utility of the model to decide whether you want to charge here or not to charge here. Above that, latent class use mixed logic model format with a latent class depends on your social demographic, such as your income and your how many vehicles in your home, this kind of information. So it helps you to distinguish different social demographic of people. And the CPT model is very different from cumulative prospective salary model. It's very different from logic model. It involves risk parameters, means that not only it considers the SOC price and distance, it also considers the risk aversion of the people, whether they want to charge or not to charge. And the final model is a Porbit model with a very complicated structure that it depends on the trip constraint and also depends on the risk level of people to consider whether you want to charge or not to charge. So 2 of my findings here is the first finding is that we found that it will systematically distort the charging decision when different SOC happens. So for the rule-based model here, most of people decide to charge at 20%, but it comes to a very different trend with mixed logic model and latent class model. You can see more, there are some people, they prefer to have a safer SOC level, then they will charge at 60% to 80%. And they show different kinds of heterogeneity, and also for the CPT and the RSBP model. And another finding here is that we can see that the general trend of the spatial temporal demand is very different according to different model, especially for station 3, which is the busiest station, and they have different demand in the peak load, and their utilization rate is very different. So my conclusion here is that forecasting the EV charging timing and also loading requires calibration to your local condition. And also you need to be very careful which model to use, depends on your variable inputs. So that's for my first presentation.
I have a lot of questions.
Yeah.
Do you have data?
What kind of data?
Real data on people's charging behavior?
No, we currently don't have that.
Okay.
Yeah, so that's why it's an uncalibrated simulation, and it reflects the originality of the different models' behavior.
But what are the models based on if they're not based on data and calibration?
Oh, what?
You have 5 different models here. If they're not estimated using data,
each model is based on the other paper's survey outcome. So they have the coefficient, and also they have all the model set up, and I just use the model set up to the Polaris.
okay, then my recommendation would be to state that all of these 5 rows or estimated models from real data.
Mm.
And you probably should even include like context about where the data came from, like what city, even sample size, things like that. Because reading it right now, it just seems like, well, you have 5 different models, and of course 5 different models give you 5 different sets of results. But if none of them are based on real data, it doesn't mean anything. But if they are based on real data, then the
The
results
model
are,
is based on the real data.
yeah, that's much more interesting.
Yeah.
How can you tell if you have such as 6 models here, right? So how can you tell which one is more realistic in?
I think the next step of my research is calibrate with the real data and the real world charging behavior. So that will help us to tell the what model is realistic. But here is just focus on the behavior heterogeneity, that what kind of input of the model and what the selection of model will distort the behavior of the SOC profile and the spatial temporal demand.
I'm also not sure you can say distort if you don't have the real data. You could say like the behavior modeling assumptions change the simulated EV charging demand.
Okay.
But since you don't know what the ground truth is, you don't know which one of them is distorting and which one's not distorting.
Okay.
So I ask a question. Can you talk a little bit more on the synthetic trip chain? And how was that done? And,
That was done in Polaris.
okay,
Yeah.
so by the software itself.
By the software itself, because we have the input of the people information, and we will give, they have already embedded with the trip chain function, generation function. So under that, depends on your social demographic and your your vehicle settings, that it will automatically generate the trip chain for each agent.
So I have never used the Polaris.
Mm.
It looks pretty popular now. But how accurate, this is also synthetic and also simulation, right? Do you have an idea how accurate the synthetic trip chains are, or do they have any kind of a technical reports?
Yeah, they
on the
have.
accuracy and so on.
I think they have a technical report, they have a paper to elaborate how they generate the trip chain and also which model they use. I think they are using one specific logic model to do that. And I think in that paper, they report the accuracy of that.
Okay.
Yeah.
So I think there's a question.
Yeah, I think Elisa have a question.
Online.
Yeah, online. Elisa,
Hi.
can you?
Yes, great job, Chenyu. I just had a recommendation. I agree with Professor Hyland's suggestion to talk more about the survey data, but I realize you might not have a lot of room on this poster. Sometimes people include like a little QR code if there is a preprint that describes the survey design and data collection in more detail. You could maybe include like a QR code to link people to learn more about the data and the survey.
Okay, thank you.
Thanks.
Yeah, I have 2 questions. So what is SOC? Do you have any definition in the paper? What is SOC?
SOC is state of charge, means the battery level, current battery level of the vehicle.
Please tell chat.
State of charge.
State of chat. Okay.
Yes, it means that the percentage of the battery remaining in your vehicle, like 20% of the battery or 30% of battery.
Okay. Yeah. Maybe is there any definition for SOC in this poster?
Yeah, I think you start with the acronym, you
Yeah.
should probably start with defining the acronym, even one like SOC.
You define the TOU and others, but I don't find the definition for the SOC.
Oh, okay.
Maybe it's better to include the definition.
Okay.
And so, what kind of choice behavior do you model through apply models? Is it a
The choice behavior is charging choice.
Charging
Whether you want to
choice.
charging at this station or not to charging at this station.
okay? When do the agents choose?
Yeah, that's a good question.
When do the agents choose when the charging? charge.
Can I try to ask it another way?
Yeah.
So like Polaris is a dynamic simulation, right?
Yes,
Is it every 6 seconds you consider where and when to charge?
no, it depends on it depends on your activity. That whether your activity is flexible or not flexible, and your current, whether you want to split the activity to charge at here or not to charge at here.
And you make the decision once you get to your activity location?
Yes,
Okay.
So every time a trip's completed, then you call this module.
yes.
Right. Maybe that can be clarified in the details.
Well, and the different variables maybe that you consider for deciding if the eight.
Kind of has it there, right? Data charge prices. One last question? Thanks, you're very good.
Thank you.
Me, you're next. Okay. Our next presenter is Amin Akbari, a third year PhD student. Also working with Professor Matthew Dean. We will hear about his first study, which is also about EV charging. Wait till you're gonna plug yours in.
Yeah, I just want to wait.
Yeah, just stop the share.
Okay.
We'll stop you right before you start.
It's clear, right?
Looks good to me.
I can zoom,
Yeah,
but I don't know if it's kind of laggy.
Come to you.
I don't know if you want, okay.
I think you don't need to until we get to like the table. We can't really.
Okay, yeah,
Good.
that's a good idea. Oh, okay, so hi again, everyone. My name is Amin. My PhD candidate here, working under the supervision of Dr. Dean. So today I'm presenting our research paper, our poster on electric vehicle charging as a monthly budget, essentially how working Americans allocate their charging session across home, work, and public locations. So this is also a collaborative project with Dr. Asmussen from University of Tennessee, Knoxville. And yeah, so let me walk you through the what we have done and what we have found basically. So let me start with some background. EV adoption is growing rapidly in the US, as we know, right? We went from about 10% market share in the new sales in the 2023. And projections suggest that we'll hit 20% in 2030. So as more people drive EVs, understanding where and how they charge become increasingly important. So now when we look at the data, home charging dominates, right? It accounts for about 80% of all charging events, and that makes sense, right? You plug in overnight, electricity rates are lower. But here's the thing, about 1/3 of US households currently cannot install the home charging due to like parking constraints or like, rentals or just cost of the upgrade. On the other hand, workplace charging is the second most utilized option, around like 15 to 20% of events. And it actually works really very well because, your car sits there like for 8 hours and which aligns perfectly with the grid. With level 2 charging actually. So public charging also is traditionally a backup, only about 5% of the events these days, but its roles is evolving as fast charging networks expand. So here's the gap we are addressing. How do EV drivers allocate their monthly charging session across these 3 locations? So, and the reason behind that, most existing literature, treats this as a single location, single discrete choice. You pick one location, but in reality, people charge at multiple locations within a month, making trade-off based on the cost or infrastructure or these kind of stuff. So moving to the next section, so what we are contributing with this study. So three main things. First, we identify the variety of factors such as demographic, residential, and infrastructure factors that explains how EV drivers allocate their charging across these locations. Things like, do you have a private driveway? Do you have solar panels? How old are you? And those kind of things. Second, we test for satiation effects, which I'm going to explain a little bit more at the methodology. And basically, does the value of an initial charging station at a location diminish as you use it more? For example, if you're already charging at home for 10 times per month, how much do you value the 11th session? And third, we translate these models parameters into actionable insight. At least we try, not just for academics kind of thing, but for employers thinking about workplace charging programs, urban planners, or utilities. So how we did it we deployed a survey last year from April to June 2025. I mean this year, and across the US. So we used the online, platform to gather the data, Dynata and Prolific, if you heard of. Participants also were paid like about $14 for about like 30 minutes of their time. So to be eligible though, respondents had to own or currently own at least the EV at least, and of course be a US resident and 18 or older. And also, they should be like kind of have some kind of employment, either a student, part-time or those kind of things. So after removing all those incomplete responses, we ended up with like 881 complete responses. And as you can see in the little heat map, most respondents, most EV drivers that expected from in the state of California, Texas, Florida, Pennsylvania, and like Eastern, the states after that. So moving to the second column, the central insight here, in my opinion, and it's really important, that is the charging allocation is actually a portfolio decision, not a single choice, single location choice. The majority of EV drivers, as you can see, distribute their monthly charging section across multiple locations. And let me just walk you through this the Venn diagram. Zoom a little bit more. Will be better. So as you can see here in each responses, by the way, it's also connected to our stated preferences experiment that I'm going to explain. That how we actually created that model. So each respondents, first of all, completed 3 stated preferences. We a task basically giving us like 2,643 choice locations. And so home charging dominates overall. About 97% of locations include some home charging and averaging 99.3 sessions per month. Workplace is next, and then it's public, which kind of expected to the current trend in the US. So let's also talk about a little bit about their experiment and attributes. The distinct characteristic about this extended preferences experiment that is kind of not traditional. That first of all, we have like different levels for each attribute across different locations. Like for example, look at the charging speed. We have like 10 to 30 miles per hour for home, but for workplace or public is actually different. Even though for public, the charging speed is kind of tied to the charging price, which we wanted to make it kind of real world experience. You get more faster charging speed, you have to pay more, right? And some of the attributes are actually like fixed in some location, like for example, in the at home, you don't have like a waiting time, right? Or if you don't need to like swap your vehicle, meaning that when the charging is finished, you have to relocate your vehicle after that, right? So we don't have that. at home or some other things. So it brings the question that how we should actually model it. So if we go to the next section, there we go, methodology. So there is a framework called the multiple discrete continuous extreme value model, or MDCV in short. So this model is actually ideal for our context because it captures two decisions simultaneously. First, the discrete choice, whether or not to use each charging location at all. And second, the continuous choice, right? Given that you have chosen a location and how many stations do you allocate there. So the model also accounts for satiation effects, through this utility function, as you can see. The key idea here that as you allocate more session to a location, the marginal value of that each additional session decreases. This is a gamma actually parameter that you can see that converts how quickly you get saturated at each location. And the baseline preferences, the size, it's a function of individual characteristics or alternative specifics, attributes and like residential demographics, all of those things. And importantly, all of this is subject to the constraint, by the way. The total session allocated across home, work, and public must equal the respondents' typical monthly charging budget. So we are really modeling how to distribute a fixed number of the charging sessions across their available option. So moving to the third column, I think I need to familiarize it. Go. Yeah. So what we have found. So let's look at our setup. Okay. Let's look at our first set of results. The factors that influence the charging allocation at each location. And it's actually a very, very big model. I just highlighting those results that I started with like important. And so starting with residential characteristic home charging, as expected, having the private driveway, owning the single family detached home and having the short commute under 10 miles one way, all increase the home charging allocated preferences. So solar PV owners also have a higher preferences to home charging, but interestingly, when we look at the satiation effects, household with solar PV plus paired with the battery storage actually allocate fewer sessions at home. Maybe they seem to diversify more across locations. For workplace charging, employers at large offices with 100 or more employees show higher workplace charging preferences, as do those with across for free charging, even when parking slot is required. That's interesting, in my opinion. And young adults, 18 to 34 years old, also prefer workplace charging more. On the negative side, Tesla owners show some resistance to workplace charging, right? Possibly because they have access to supercharger network. And for satiation, older adults, 55 plus years old, show like persistent workplace charging habits, and employers become less price sensitive as they charge at work, as they more charge at work, basically. For public charging, women basically show higher preference in public charging, as do people who combine charging with other activities like errand or, doing other trips. You're not going to the public station just to charge and sit there. You're trying to align it with some other activities. And yeah, that's basically on the negative side, higher prices, which comes in bundle with the faster speeds, reduce the public charging preferences. And moving to the next, almost last outcome, all right. So we have identified what factors matter so far, right? But how much do they actually shift charging behavior? So that's what average treatment effects, shows us. These numbers represent that the percentage change in monthly sessions, right? In monthly session allocation. When a factor, for example, like home charging, shifts from one condition to another, and we are holding the other, everything else basically. So let's, for example, like talk about like charging for workplace charging price. I think it's huge, and where workplace charging goes from like 45 cents per kilowatt hour to free. We see like 22% increase in the workplace charging allocation. That's largest policy that kind of we have found. And importantly, those decisions also come from somewhere else, right? They would allocate less for home charging and public, right? And for example, looking at the solar, whole household with solar PV allocate 22% more station to home charging compared to non-adopters. They receive that electricity, as essentially free, right? So they anchor their charging behavior around the home. But here's the twist: when you add the battery storage, solar, the effect actually reverses. The battery, captures the solar production, whether the car is there or not. So these helps actually try to diversify away from home, maybe saving that energy stored for something like more important for their utilities, their home alliances or something like that. And yeah, moving to the last part, what's our conclusion? For example, we can. For employers, we could say that free workplace charging is the most effective lever that you have to increase. That it will increase the utilization, and at 23% almost boosting substance. It's kind of massive. And the satiation effect also we found that suggests that once, for example, especially for workplace price, if you look at it, that means that workplace, more when the prices increases. Obviously, less people would try to allocate a charging station out there, right? But there are some employees that they need this workplace charging. So, and the satiation effect is positive for them, meaning that no matter what, that you increase the price, they still stick with this workplace charging. So that might be important for workplaces. They may, for employers, they may use it to maybe they increase their revenue. And on the other hand, they just do some trade up with providing some other amenities for their employees. And for planners and utilities, you could say that urban residents shift significantly towards public charging. Infrastructure, maybe investment should be reflect this reality. Public charging isn't just a backup option for urban residents in the cities. Maybe it's a core part of their charging portfolios. And yeah, here's come to them, and thank you so much for.
Is there any factor affecting kind of waiting time for charging? Some kind of queue?
Yeah, there was a waiting time, and if you look at the table, the attributes, the waiting time is actually parking space convenience. Actually, I haven't included waiting time here, but it wasn't actually significant. We don't have waiting time in home, right? And only we have waiting time at workplace and public. But
usually, which one is more severe waiting time? The workplace or public? Which one is more?
Well, definitely it's not in the public because the reason is kind of clearly obvious because you probably choose which public station you would go beforehand, and you have a kind of background idea what's going on in that public station. If it's actually crowded or not, how much is the waiting time? Usually not the first time.
Often online they'll also have
Yeah, they have
open.
Exactly. So it's not that big of a deal. But for workplaces, that could be when they increase the demand, more EVs comes to more people adopted the EVs, but it's still maybe because it's still it wasn't significant the early days workplace charging, so maybe the future.
I have a question. For the continuous choice, how many stations? What does the station mean here?
Satiation?
Station, continuous choice. How many stations to allocate? What is stations?
Oh, the session. Okay, the sessions means the one charging event. And for example, doesn't matter. Charge your vehicle 20 minutes, we count it as one session.
For instance, how many stations each person is taking?
Yeah.
Like for home, workplace, and public.
Yeah.
One more question, the outcome table two, is it from the NDCEB model or?
Yeah, it is from an NFC model basically, but it's kind of sensitivity analysis that you do with the model. And when you get your model, you know, you hold everything. For example, you focus on one variable, you hold everything else constant, and you only change that variable. I mean, usually from in this, within the boundaries from most severe up, level to the like another level. So yeah, this is the kind of sensitivity analysis.
One more question. Those variables like home charging price, solar plus battery, did you ask them in the survey? Okay.
Yeah, so this survey is kind of massive, 30 minutes. We asked a lot of questions. So we asked if you have a solar, it's per liter battery. If you don't, I mean, if you use that battery for using what use, for that battery and those kind of stuff.
Okay, but that was not a part of the choice section, right?
No. The experiment is only basically the table. Yeah.
And one more last question. That comparison A to B, what's the A to B?
That's a platform. Good.
Elise also has a question.
So you can ask this. You can ask this one. Sorry, I didn't mean to.
No, what
was your last question?
That comparison A to B, I was confused. What is A to B?
Oh, A to B means the same question, for example, from charging and recharging to the maximum price.
Professor Borowski, Jeffrey Kotaro.
Did you call on me?
Yes.
Oh, okay. Thank you. Yes, I was interested in the finding about women have a preference for combining their charging with other activities. And I think that comes from your choice experiment activity level, other activity leave vehicle. I was just curious how that was described in the choice experiment. Like how far from their vehicle are they actually willing to walk away? And can they actually conduct maintenance trips during that time, or how is that done?
Yeah, for public, I think we never asked them that if you have to. We didn't like start. We saw that it doesn't make any sense if you just walks through the public charging and how far it is. But we do ask them for the workplaces, not in the experiment. We do ask them like, if there were chargers available in your workplace, how far it is, from your entrance of your building, for example, right? It's actually kind of mattered at first. It's kind of the large model. I couldn't present all of the attributes here. But for public specifically, I would say no. But workplaces, yeah, I think it's significant. Not for women, I think for all the employees, yeah.
Thank you.
I was just curious if maybe you could add a legend to your map because it does say number of respondents by state, and I just can't tell. Is it 0 for North Dakota? Is it
Yeah, it was only
for
2 states actually. It was 0 North Dakota and Ohio, I think that's so. But overall, it's not the main focus of this one, to be honest, because you cannot compare it. Yeah, what's it National House of Drivers, because National House of Drivers only not EV drivers, and the EV drivers, kind of mass survey across US haven't done, but it's still, I think it's going right now. They're doing specifically targeting EV surveys. I forgot what is the name of that, but it still doesn't matter because we cannot compare it to the some bases. This is the US EV drivers here, so. But it's kind of in the same range of the other studies, you would say. They usually work with this number of the respondents as the US.
How many models did you estimate? So it seemed there were 3 models for each place.
No, this is actually one model.
One model.
Yeah, but it's captured different locations.
Okay, so is it a nested model?
No, this model is here, the methodology. Here.
No. I mean, so there can be 8 alternatives. So one person choose home, workplace, but not.
No. Okay, so imagine like this, so this is survey. I'm giving you the home, workplace, or all of them at once.
Yeah.
Right. Also, you choose. I mean, you don't actually choose each location. you allocate your charging. For example, with this attribute, maybe home is cheaper. I allocate like 10 sessions per month for that. For workplace, 5. For public, maybe 1. For example, right? But it's actually the maximum. You cannot put a number. The maximum, the max total is actually tied to constraint that with the question that we asked earlier from them, what's your monthly charging session? For example, you say like I only charge my vehicle 5 times per month, right? Then we say in the experiment, allocate this 5 sessions across different locations based on different aspects.
I would include that on the slide, because it's not clear what context they're making the decisions.
Yeah, I was thinking about that, maybe just putting some like question sample, you know.
Well, yeah, I mean, it's up to you, but like,
Yeah.
I'm sure you had something in the actual survey where you say like, you told us you had 7.
Yeah, I did, yeah.
So just copy and paste.
Okay.
There you go. Yeah, that was basically my question too. Is
Okay.
what is the context of the decision? But you answered it. All right, thank you, Amin. Great job, audience. Okay. Our third speaker is Kotaro Yamada.
Yep.
Who is hard to count how long he's been here. Not that he's been here that long, but he was here for 2 years.
Yeah.
Took a couple of year break, and now he's back doing his PhD at Professor Jayakrishnan. Excited to hear about the updates since your qualifying exams 9 months ago. So please welcome Kotaro.
Hey, thank you for coming and thank you for the introduction. So I'm Kotaro Yamada and fourth year PhD student. So I'm presenting my research theory titled Solving the Activity-Based Pickup Drop-off Problem for Demand Responsive Mobility Systems. This is basically a big overall numbers for activity travel activity patterns in our sweep chains. I propose a methodology to evaluate demand responsive mobility services such as microtransit and TMC, even taxis. So I formulated the activity-based pickup and drop-off problem in short ABPDP to consider activity participation of passengers, which is not included in the previous DLP models. But this problem is hard to solve, so I developed a solution algorithm to solve it efficiently using a giant tool representation by some researchers. And I solve problem instances with hypothetical data I simulated. And I investigated the effects of travel demand density and ride sharing on the performance of the DLT system. The demand responsive mobility, I hear the definition for the demand DRM, which is car-based, non-fixed route transit. Someone obeys. But I excluded the peer-to-peer option here, where people, drivers have their own itinerary. And I assume microtransit type service first of all. So DRM is very prospective choice for the transit operators to replace their transit systems to improve the efficiency of the system. and to fill the gaps in the current systems. But it has some benefits. Supposedly, it will improve the accessibility and equity of the transportation, and it may reduce environmental impacts as well. But as as mentioned in several articles, BMT is possibly more than private vehicles, particularly in case of TNC, and many microtransit systems are less viable because they cost a lot. They fail very soon in many examples. So I tried to evaluate the viability of the DLM systems using the BLM, using the BLP, and what characteristics, what situation is favorable for the DLM system, and I derived a methodology, and I assume that the system is a pre-booking based system, which is more efficient than dynamic routine dynamic request system. And for this research, I should have added that in paper in this section. The existing methods are only trip based, and mostly they mostly use PDPW or diagonal right problem, but they don't consider the activities. They only consider trip attributes. The most relevant work is done by Mahmoudi in Phoenix. They use the time discretized network, but we refrain from using this representation because although they are advantageous to deal with time-dependent attributes, but they might be computationally challenging if we consider the high temporal resolution. My methodology, ABPDP, is based on pickup and delivery problem, but I explicitly consider activity duration between trips. So I added one constraint to consider the activity duration to ensure sufficient activity participation of the passengers. This is an entire route constraint, which is not really considered in the previous VLP. So for example, if one person is served by two vehicles, the two vehicles should consider the activity between two trips, you see. So those two vehicles should coordinate with each other. So the solution of the ABPDP is the optimal route to support passengers' travel activity patterns rather than individual trips. I developed a solution algorithm based on the column generation algorithm with some heuristics. The column generation algorithm generates multiple routes, feasible routes, and find the best set of the routes that serve the given request. So the algorithm requires some heuristics to generate feasible routes. I used 3 heuristics. One is based on merge heuristics proposed by Xu for general PDP TW. It merges existing routes into one route to make a more better vehicle route. The other one is local search in the giant representation, and that I focus on developing this heuristic. I use the giant representation, which is just a sequence of multiple moves, but they are jointed through dummy links. By using this representation, we can consider the inter-route constraints as inter-route constraints. So we can use some heuristics developed for the previous problems. We can apply other local search algorithms and other heuristics through this presentation. I developed a local search algorithm which just shifts some requests to other positions of the giant tool to find the better set of the moves. Okay, so the algorithm basically iterates, improving the existing roads, vehicle roads, to find the best one, and until we find the best one. Not until, but yeah, try to find the best one. I iterate the algorithm for several times and finally find the best solution to the given TAP activity, travel activity patterns. We implemented the algorithm in a hypothetical situation, which is the 10 by 10 Manhattan, 10 by 10 miles Manhattan grid with intersections located every half miles. I deploy on the center with 10 passenger vehicle. I generated many activities in the network and also I generated travelers in the network and assign 1, 2, 3 activities to each traveler and allow them to make activity or trip chains, visible ones. And the objective function is cost total operational cost, and considering fixed cost of vehicle and per mile cost and driver wage as well. I conducted 3 experiments. The first one compares the 3 heuristics. One is the previous one, existing one, and the other one is mine, and the combination of them. I found that the combination of them worked better, the best among them. So I only use the heuristic 3 for the following experiments. Experiment 2 examines the effect of demand density. I found that demand density is necessary to reduce the cost per request. And also it lowers the VMT than private vehicles. Private vehicle, I assume I compare the BMT compared to the VMT of the simulated TAPs. Finally, I limited the ride sharing of the system and found that ride sharing is necessary to reach VMT reduction, even with the DRM services. Okay, so yeah, I investigated the demand density as well as the necessity of the ride sharing to reduce the environmental impacts of the DRM system. Okay, yeah, there are a lot of limitations of this research, so I need to improve the algorithm because even with the heuristic 3, it took a lot of time solving one problem, particularly when the demand density is high. Also, I should consider some operational strategies such as root deviation or point deviation or multimodal for these systems. And yeah, this model should be collaborated with the demand models, which consider the stochasticity and some adaptations of the RM system and interactions with the supply side. Okay, and that's my presentation. Thank you.
Explain the column generation process more because I didn't get what is your objective exactly. How did you do the pricing? What is the cost there? I didn't get the column generation.
Okay, so column generation. First of all, we have the feasible set of the rows and solve the master problem to find the best set of the routes. It's a tentative solution for the master problem. And based on the tentative solution, we can compute the reduced cost for each route. And based on the reduced cost, we can generate the additional routes, which may be the better ones. And I included the additional routes to the master problem, and then we solve.
What's the objective?
Objective is the operational cost. So I try to find best operationally best set of the solution, which may not be best for the users. Richard means raising hand.
Richard, you can unmute yourself and ask your question.
Hi, Kotaro. Great presentation. This is looks like a very nice framework. Still trying to wrap my head around your framework. So I was wondering, like, in the figure I guess the first figure, how do you implement it in a network? Like, do you put a specific link between the two routes? How do you implement the activity in the network?
Are you asking about the third column of the hypothetical setting?
No, the first diagram, vehicle 1, vehicle 2. Yeah, this one.
I asking the computational thing or coding?
Yeah, how do you model it? Like, how do you model the route?
I just did a Python and the Cplex to solve the problem. And is that the answer for you?
I mean, I'm asking about network modeling. I mean, how did you model it in the graph? Did you use any?
This one?
Yeah.
I just draw it by hand.
Okay. Perhaps okay. Okay. So I have another question. So so the routing is happening between one route to another route. In between there is one activity duration. So if there is one central operator who is doing all this routing for the vehicles, how does the operator perceive between the two routes, because there is one activity between the two? I mean, is the routing decision comes from one single operator for both the vehicles for the same rider or request?
Okay. So there's one operator with multiple vehicles. The operator knows every trip change and activity.
Okay.
So that information is given to the operator through a certain system. So there are a bunch of travelers who are required to input their schedule of the day. And that schedule I simulated hypothetically. Okay. But that can be done through web systems, possibly. And if the operator knows the shape information as well as activity information,
I see.
But-
Okay, got it.
what should they do to ensure the sufficient or requested participation of the activities? That means travelers should provide their minimum activity duration.
Okay.
So isn't it the case that like right now you just make 2 requests?
Right? Yeah.
So is there a lot of value to having them provide their activity duration?
Basically, maybe operator should ask for time windows as well. For the arrival activity and the duration. Or how long do you want to stay there?
But do we need to know that? I mean, you can, if I made 2 requests, you could figure out how long I want to be there.
How long? Okay, so if someone commute to the workplace, maybe they know how long they want to stay there. But maybe there can be a suggestion by the operator. This place might require 1 hour or 2 hours if the traveler is not familiar with the place.
Any other online questions here?
No.
So you said the computational costs pretty high because you were using evolution. Evolution.
Observation? Yeah.
Algorithm.
Yes.
Yeah. So did you consider any other? I know that evolution theorem. Algorithm. Is one problem. Any other better methods? Or
I mentioned the genetic algorithm.
oh, genetic. Sorry, yeah, that is the word I was searching for. Yeah. Genetic.
Yeah, there are a bunch of heuristics that we can apply to improve the routes.
Okay.
So I used a very fundamental, basic search, which is local search. Yeah, it's a kind of brute force method.
Okay.
So I tried every possible position of the request within the route, which is not really computational. Maybe we should include some stochasticity in the search. And I agree that the search algorithm can be improved by considering some better ones.
Yeah, because I'm asking about this. I mean, the genetic algorithm has been used, to solve this kind of problem for decades.
Right.
But now with a lot of machine learning and those you mentioned about stochastic searching.
Yes.
So I'm just wondering whether there might be more efficient methods to solve this. I think that would be really cool.
Because this is very, as I said, fundamental and very basic.
Once you guys have contributions of these methodology, right? This is a new methodology.
Maybe the second heuristic can be a methodology, I guess. And I was also thinking of the effect of the activity duration on the DRM performance.
Yeah, because it seems better to emphasize the contributions of the
Right.
posters. So
Yeah, I will include that in in the next version of the presentation.
All right, let's thank Kotaro.
I think
One recommendation.
We're really out of time.
Yes.
Well, you guys can talk
Okay,
right
yeah.
now, or you guys can talk afterwards. Okay, our 4th presenter, is Shaqa Nouhi. My PhD student, although this research has nothing to do with me, was doing her master's at the University of Minnesota with Professor Michael Levin. Welcome, Shaqa.
Hello everyone, as Dr. Hyland mentioned, and this is one of my projects during my master's degree from University of Minnesota. The title is Bi-level optimization of detour signage placement on the road closures. Definitely all of us have seen some detour signs during construction season around construction zones. These detours actually are designed in order to reroute ourselves into some better routes because those primary routes are under construction. Actually, these detours are designed in order to avoid more congestion or decrease the travel time of users. But probably none of us have seen some specific detour signs for trucks or heavy vehicles. Why am I emphasizing on trucks? Because even if we don't have any heavy vehicle or trucks in traffic flow, imagine that the load of traffic during detour would extremely increase on some replacement roads that are replaced by those by detours that are for those roads that are under construction. But imagine between these cars, there are some trucks or heavy vehicles that they want to switch to some other roads that are not even appropriate for this extremely heavy load. And based on an actual report, there's a rule of thumb called power of 4, which means that if a truck is 6 times, for example, heavier than a car, the damage that it can cause to the pavement is 6 in power of 4 compared to a car. So it's really important to think about during construction how we can plan detours specifically for trucks in order to minimize the damage that they can cause to the replaced roads. The main objective of our project is to minimize the utilization of some truck restricted, or some, better say, vulnerable roads for trucks. As the topic of my research shows, it's a bi-level optimization, so we have an upper level and also lower level objective function. Although our main objective is minimizing the utilization of trucks from vulnerable roads, at the same time, we want to keep the efficiency of our network. We want to keep user equilibrium traffic assignment at lower level. So the lower level objective function is a standard Beckman function and other standard constraints for flow and demand that you can see here. We have some convergence metrics, total system travel time and shortest path travel time. How we can track that user equilibrium is doing well is that total system travel time should get closer and closer to shortest path travel time, and the gap between them should get close to 0. Now it's time to talk about the upper level objective function. As I said, we want to minimize the truck usage from some vulnerable or restricted roads. How we want to show this usage is using some truck VMT formula. And because here in the upper level, we want to focus on truck flow, we have to solve the lower level user equilibrium with a vehicle specific type, which means that we need to track flow of cars and trucks separately on each link. Actually, the output of user equilibrium from lower level is X of trucks and X of cars on each link separately. The upper level objective is a summation of X of trucks multiplied by a binary attribute called y of ij multiplied by length of each link. What is this y of ij? It is a binary attribute we assign to roads as if some of the roads are restricted or vulnerable, we assign y of 1 to them, and the rest of roads that are rest of links that are appropriate for trucks. Trucks are free to use them during construction. We assign 0 as y for them. So actually, the output of this upper level objective would be just for those truck restricted links. Now the question is that how this upper level and lower level are going to be integrated with each other and are going to be in touch with each other. We did that through travel time function. We use BPR function for travel time with a little small modification. Our decision variable here in this problem is a binary decision variable for detour signage, and it is called S of ij for each link, which means that in upper level in the upper level, the genetic algorithm suggests us, for example, these 3 links are as suggestions for detours. So S of ij of these 3 links would be 1, and the rest of links would be 0. The BPR function for these 3 links would be less than the BPR function for normal links. Why we did that? We did that because we want kind of encourage people to follow detour signs. It's like those, in physical meaning, it's like those detour signs that are put at the start of the streets that are a sign for people that you'd better use these roads. If you use other roads, your travel time would be increased. So it's like a perceived travel time that people who are using detours would experience. This gamma is 40% of BPR function, which means that for those links that they are suggested as detours, their travel time would be 60% of BPR function. And I forgot to mention that the upper level objective is being solved with a heuristic method of genetic algorithm. Now I'm going to talk about results. The initial results that we got was results without considering the upper level at all. First, we wanted to make sure that our user equilibrium is working great on our network. And I have to mention that the network that we tested our model on is network of Minneapolis, because this project was a project from Minnesota Department of Transportation, and actually they asked us to present results on network of Minneapolis. As you can see here in these 2 figures, we can see the performance of user equilibrium. You can see TSTT is getting close and converge to SPTT, and gap is decreasing until getting really close to 0. The next thing was that we wanted to make sure that whether we are able to track flow of cars and trucks separately on each link or not. Still here, until here, we are not adding any upper level or genetic algorithm. Here we closed some of the links in network of Minneapolis. The blue links actually are those links that we selected them as closed links, and the rest of colored links are color-coded based on the increasement of traffic truck flow on them. So you can see that how closing some of the links in blue is influencing surrounding links and increasing trucks in other links. Now it's time to add the genetic algorithm optimization on top of this lower level. We chose these parameters for running a genetic algorithm, and the first step was choosing a meaningful closer, because here in this general baseline, we just close some of the links to see whether the model is working or not, whether we can track flow or not. Here, MnDOT suggested us to close 10 links in one of the main highways in Minneapolis called MN36. Here is not really visible, but this is green. This green line here has been closed. And we tracked how truck flow in surrounding links is decreasing or increasing. Yellow links actually are those links that truck flow has been increased on them, and blue links are those links that truck flow has been decreased on them. The next step was adding detour and restricted roads. Restricted or vulnerable roads for trucks have shown in red thin color here. So the red links are restricted or vulnerable roads that we don't want truck to go under. Still, the green links are those closed links, and we can see that still blue links are those we have decreasement in trike flow, and yellow ones are those that we have increasement in trike flow. The four lines here in maroon color are actually selected detours by our model. There are actually 5 links, but here 4 lines have been shown. The main objective of us was decreasing trike flow on these restricted red lines, and we can see that on most of them the trike flow has been decreased. And interesting point is that on most of selected detours, trike flow has been increased, which means that that's a factor that we implement on travel time is working, and people are using detour signs more. We can see here on these detour links that trike flow is not increasing. That may have 2 reasons. The first one is that the increasement in trike flow may be really small that we ignore it. Or on the other hand, sometimes people don't follow detour routes that can be happening in real world too. So people are not following this detour link, and trike flow is not increasing on them. And here the last result is fitness function over generation. Fitness function is this objective function of upper level here. And you can see the VMT on restricted roads is decreasing from 26 to around 20 vehicle mile per hour. And because we selected a number of generations in genetic algorithm as 3. The computational time was around 32 hours because the user equilibrium has been solved for 48 times. And if I want to conclude my research, the bi-level user equilibrium genetic algorithm framework can successfully select detours in a way that can actually minimize or decrease the fitness function on restricted roads. The VMT of trucks on restricted roads decreased around 23%. And this method is computationally feasible for a very large scale network as we run it on Minneapolis network. And the final thing about this model is that this framework is really feasible, flexible, and it can get better more because in this project, we added 2 constraints. The first constraint was detour budget constraint. For example, we said for this segment of closer, we only want up to 6 detours. So you can change them by your budget. For example, if you don't have any budget, you can have as much as detour signs that you want. Or even decrease this number. And also another limitation was that we told the model that you can only choose detours in the radius of 3 miles of the closer. So it only searched in 3 mile radius of this closer to find appropriate detours. So you can change it by your needs. As I said, this project has been funded by Minnesota Department of Transportation. I'm done. Thank you for listening.
So when you convert the vehicle size PCE, something like that, same factors for the only normal vehicles versus truck. Like you have to convert for the car lengths, how these lengths affect to the load, right? So there's some factor for converting vehicle to the impact of these vehicles into the roads. Because I think that the impact for the road can be different, depending on the vehicle types.
Yes. I didn't get your question.
Okay, so I'm not sure as well. So I will,
If you mean here, we are just using flow of trucks. We don't care about, in upper level objective, we don't care about car flows.
Yeah,
So there's no need to add another factor specifically for trucks.
because my thinking is that the impact of each car on the road is depending on the size of the cars, right?
Yeah.
So, yeah,
If we imagine all of the trucks as same truck and categorize all of the cars in category of cars. Here in upper level, we don't care about cars and we assume all of trucks are same size and they have some huge impacts on pavement.
I just have a question about how do you interact with lower level with upper level? Because I see that you have the travel time, but it's not at the upper level objective function. And I'm just wondering about how do they interact? And do you have any constraint for the Yij, which is a binary attribute? So what does that mean? And I didn't see any constraint on the upper level. So I'm just wondering how that will influence the final performance.
The way that the order of this process would work is that genetic algorithm choose randomly some links as detour suggestion, which means assign Sij of 1 to some links, some of link ij, and give this actually binary 1 and 0 to traffic assignment. Traffic assignment receive this binary 1 and 0, and during calculating BPR function and travel time for each link, it consider that for those links that genetic algorithm says these are detours, it calculates 60% of BPR function instead of the full BPR function. But for the rest of them, for example, if just 3 of our links are detour, for the rest of links, we just use the normal BPR function. This is how they are integrated. So the output of user equilibrium would be flow of trucks and flow of cars. We just care about flow of trucks. We get flow of trucks, enter them into fitness function. Again, we go to genetic algorithm. Genetic algorithm get x of trucks multiplied by Yij multiplied by length of link and find fitness function. At the next generation of genetic algorithm, it decide to find a better Y combination from the previous generation.
S combination, right?
S combination.
Not Y combination.
Yeah. Sorry. S combination from the previous generation in order to make this fitness function decrease. And now about your question about Y of ij. Y of ij is an attribute. It's not a variable. It's completely from our data. For example, we decide that this red long line is restricted or vulnerable. So we set one column called Y of ij or vulnerability as 1 instead of 0 for these red links. So this is just coming from data. Thank you.
One more question?
So you said that you're using the BPR function.
Yes.
But I see this as a very dynamic problem with the Q spillback, with all of these things. BPR function generally is for kind of long-term effects, definitely without the interaction among different links. So I'm wondering how this would impact the
this
overall
has been solved
performance.
completely static. We got demand for duration of 1 hour, so the demand is completely static. This is for around, I guess, from 6 a.m. to 7 a.m. of network of Minneapolis for each OD pair. So everything is static. That is why that we use BPR function. The future work and more complicated work of this project can be dynamically, for example, get dynamic demand data during all day, and instead of using BPR function, use some, I don't know, other traffic flow modeling.
Thank you.
All right, Chenyu back, and we're hearing about LLMs for the first time today. So we made an hour and 40 minutes without hearing about LLMs. So now is the time.
Yeah. Okay. So this is my topic about large language model, and I want to use large language model to improve the behavioral interpretation. Especially we are most using large model and any utility function today. So it helps us to understand that why people choose a certain method or certain technology. So the background comes that in transportation that we are good at predicting what people choose, especially come to some state preference survey and discrete choice models. But it's very weak for this kind of model to explain why they choose it. Especially different people have different heterogeneities and they have different motivations. So the traditional SP survey and discrete model, choice model, just give us the average effect by the coefficient, but it didn't interpret that whether a certain demographic group or certain group of people why they choose another method or another technology. So large language model by generating reasoning-rich explanations that it creates a opportunity for us to infer what is the real preference of the people. So here is my opportunity to do this research is to bridging the reasoning with the econometric models. And also I'm doing the equity auditing means that we want to know whether large language model do accurate job to classify the people from each other in their inference. So I propose a large language model behavioral modeling framework, and I integrated with older logic model to complement one to another to capture the within group behavior variation. And the final thing is that I use fairness matrix to evaluate the large language model's preference, whether they are equitable or not equitable in a transportation survey context. So here comes my methodology here that I input the survey data into the prompt generator that I see that it that I see here that I generate a prompt that imagine that you are a smart charging analyst and your task is to infer the interest level of the people adopting smart charging. And it will give you the user message about your demographic, your housing ownership, and a lot of information from the survey with different three prompt designs such zero shot, chain of thought, and self-consistency. And that can help us to have the final output about the people's interest level of smart charging and why they choose this interest level. So by this, we can use a cluster-based older logic model and fairness metrics to evaluate the output of large language model. Here is the data and the background we use for this research framework. So we have a US survey with about 1,000 adults, and we link their social demographic attributes with smart charging preference. And we input this kind of information into large language model to collect the final outcome of the final output of the large language model about their interest level and their perceptions, the explanation of their perceptions into the 5-point Likert scales. And the model we use here is GPT-4o, and we use 3 different prompt designs and output the Likert response and the natural language explanation. And by doing that in k-means and TF-IDF filtering, and finally cluster their reasoning into different clusters. So we generally, for each prompt, we use 3 clusters to identify what the large language model think people should, what large language model think the people, why they want to adopt smart charging or not to adopt smart charging by their backgrounds. So it generally can cluster people into 3 directions. The first direction is they are cost and environmental conscious individuals, so they are more focused on the cost, and also they are more focused about the environmental friendly behavior impact on the smart charging. And the second cluster is that people are low income and low educational, so they are pretty much like not have an idea about smart charging and why they are important. And final cluster is about the large language model think that people are more environmental directed, so they think that they think more about the environmental impact about smart charging in this case. So that's the cluster I classify from here. And two outcomes I got from logic model and the matrix is that here is a snapshot of the zero-shot prompt design older logic model compared to the no cluster model. So here we found that the older users shows that low interest in smart charging, especially even though they are more environmentally aware, they are still lower interest in smart charging. And for the high educated individuals, so they are important. They show some environmental attitudes in the cluster-based older logic model, but their attitude is masked in the full model. And so you can see the differences that whether we use a large language model to do the cluster or not to do the cluster. So some effect can be masked and some effect can be unmasked in the coefficient. And the last thing is that the privacy concerns are underestimated in the full model, but show significant negative effects in the privacy or risk-related clusters, which is number 2 in self-consistency prompt. So our conclusion here is that the full survey model underestimates the subgroup concerns, but large language model prompt plus the clustering enhance the insight. And another things we done here is that we use a matrix. We use 2 matrices to evaluate the equity of different prompts. So here we show that the zero shot have less bias when inferring the interest level, while the COT and self-consistency observe the large disparities, especially in education and age. So it's very big helpful to use the COT and self-consistency, while it gives us a more full reasoning chain, but it introduces more equity problem compared to the zero-shot prompting. And so that can be regarded as a trade-off for the large language model here. So that is my presentation about this poster.
Yeah, let me ask. I'm a little bit confused about your workflow here. I mean, you already got the data set of like 10-50 people from survey. With their
1,000 people from survey.
1,000, right?
Yeah.
1,050. And from survey, if I understand it correctly, you do have the social, economic, demographic data there. You do have the charging preference there as well, or did I miss that?
Yeah. It also has the survey investigated smart charging interest level. So our job doing here in the cluster-based older logic model is that we have the reasoning chain from the large language model thinking that whether they are interested in smart charging or not. And we also have our survey-based smart charging response. So we are comparing the older logic model from the large language model to the real response older logic model.
So you are trying to kind of rebuild the reasoning chain in a sense?
I think reasoning chain is to help the people to help us to understand that what is underestimate or overestimate if we are not using the large language model to do the cluster-based older logic model. Yeah, and the first step we did is.
Can I elaborate a little bit on where my confusion is?
Yeah.
So I don't get why the prompting many times is that we ask a question, they give the feedback, right? So do we prompt the data set or prompt
we prompt for each individual survey rows. means that we are regarding large language model as an agent, and they are inferring whether they are inferring the smart charging interest level
Based on,
the social demographic and other attributes of the survey.
but not based on their actual smart charging preferences.
Yeah.
Still don't quite get it.
Yeah, it's a little, I agree with Professor Jay. It's not clear what you did
Or
or why.
or you are kind of implicitly assuming you built many agents already.
I think he's just adding columns to these existing adults through a prompt. So, okay, you did clustering. You clustered the 1,000 adults, right?
Yeah.
And you clustered them based on the LLM's clusters.
I think it's that the approach is that for each response from the survey, we give the large language model the demographic and other information, and let the large language model to infer the smart charging interest level, right?
Okay.
Yeah, and it also, we ask the large language model to do the reasoning that why you choose for this smart charging level.
Okay.
So that is the text here that using that natural language to do the clustering.
Okay.
And we compare the cluster-based older logic model with the real response from the survey older logic model. So we are compare the coefficient from each other.
Do you compare the predictions?
Yeah, we compare the predictions by the DP and the TVD matrix. Whether this shows that whether the large language model is overestimate the interest level or they are underestimate the interest level.
And what's the answer?
The answer is that there are bias and equity when it comes to age and education, and it varies, depends on different pump design.
Isn't the more fair comparison to do a clustering of the original data based on sociodemographics?
Oh, what? I think here is just we are based on different social demographic attributes to compare the group. The matrix we use is DP and TVD. So
No, I'm saying like you're saying you have this like cluster model and you have a non-cluster model, right? And you eventually compare them.
Yeah.
Okay, what I'm saying is like you gave the LLM a lot of information about the travelers or about the respondents that it used to make cluster decisions, but you didn't allow your non-LLM model to do any clustering. So it's a bit of an unfair comparison, I think, to not have clustering in your no LLM model, but allow clustering in your LLM model.
Yeah. I think the model settings here is that I think I need to think about that question. Yeah.
Question, the data set at 150. So is it something you put the data set in the LLM model, like trained it, and then the data set from the US survey you have? So you train the LLM model with the data set?
Yes.
Okay. So like you put it in as an Excel, or like you write it in the language?
What do you
to train the LLM model. And
I'm not sure he did any training of the LLM model. I think he just said, here is the information for this respondent. Tell me about what their preference is for charging and why they have that preference.
so it's something the model has to read from the data set.
Yeah. My understanding. Does that sound right?
Yeah.
One more, Kotaro?
Yeah, so you said you identify three clusters, but it cannot be the number of clusters can be found by the k-means. K-means means the number of clusters. How did you find three clusters by k-means? It's impossible to find the number of clusters.
Impossible.
So how? So you should tell k-means the number of clusters.
But you can also use the Abel method and within cluster error to find that. If the k-mean cluster algorithm is that, you know that each location about you know the projection of each point in a high dimension space, and you will have the distance from each other of each point. And that can help you to understand in the center whether we choose this center or not choose this center, what the error is. And that error can help you to find the within cluster error. And we can sum it up and calculate it. And for different numbers of clusters, you will see an error number. And that can help us to see which is the lowest one.
I mean, so you try different numbers of clusters. So, and finally you found three is the best for the k cluster. Maybe it's confusing to say that you identify by k-means cluster. You used maybe k-means cluster and some error.
I think that's a whole flow workflow.
No, it's not the k clustering. It's the k cluster. It's a methodology to find the number of clusters for k cluster.
Thank you, Chenyu. Right, last, definitely not least, Amin is back.
Hey.
We're gonna hear more about charging, workplace charging in particular. So, welcome, Amin.
If you have a EV. I don't even have a car anymore, dude.
Maybe the foundation in how should either EV or gas vehicle with hybrid.
I'll know exactly.
Maybe
how to charge
you
it.
just prefer $20,000 to buy it.
Oh, yeah.
Yes, that would be great.
Okay, let's do it.
I'm actually curious about your answer after all your research. Would you buy an EV? After you know that?
Well, I mean, I would definitely buy an EV, honestly, but I mean, today they're more expensive than gas vehicles. But I think the best option, I mean, currently it's 2025, 2026 is hybrid. But I would definitely buy it here. Okay, okay, let's get started. Just gonna do it a little bit faster because we don't have any time this time. But so this paper looks at a different question as employers consider offering workplace charging, what program feature actually matters to employees. You know, specifically, we are investigating employees' preferences for managed charging, where the employers control when your car charges, and bidirectional charging for vehicle to grid, where your car can actually send the energy back to the building. So let's start with the problem. So again, EV adoption is accelerating, right, which is great, but unmanaged charging is straining the grid. So according to the Department of Energy and the National Labs on managed EV charging, okay, thank you, and could increase the peak electricity demand by 1 to 5%, and there is an emission angle, the evening home charging, which is when most people charge, produce 65% higher emission than midday charging, because that's when the grid is dirtier, you know. As you can see in the chart, this is a California famous dot curve that you can see that during the standard workday 9 to 5, that's exactly when solar generation is pushing the net load down. It could be negative, but most of the time it's gonna be wasted, right? And here's the opportunity. Over the 80% of the US job, they offer free parking, and 8 to 9 hours workday is a perfect dual time for level 2 charging to fully charge a vehicle. But here's the problem actually. In workplace charging, currently right now accounts for 15 to 20% of all EV charging events. That's a massive missed opportunity. And this is where managed charging and bidirectional charging can come in, but the gap is we don't really understand that whether employees will actually accept this program in the US. And no study actually at this time looked at it. But there have been some studies in other countries, especially in Europe. So what we are contributing, two main things. First, we identify the program attributes that actually drive employee acceptance of managed charging and bidirectional workplace charging, especially in the US context. And second, we quantify the trade-offs between attributes. That this gives employers actually practical and guidance. If we can, for example, we can offer free charging, what else you can adjust to still hit the participation target, for example. For our data, we use the same kind of workplace charging survey as I mentioned in my first presentation. And I don't need to go through it again. So let's look at the second column. So we ran two separate aesthetic preferences experiment, one for managed charging and one for bidirectional charging. So each respondent completes 3 choice tasks per experiment, choosing between 2 program attributes with randomized attribute levels. So this gives us like 2,643 choice observation for analysis. Let me just go through, walk through the attributes that we have varied. I can't leave this zoom in. Yeah. So for managed charging on the left side, we varied 6 key attributes. These are the attributes that highlighted in previous studies, by the way. That's why we chose them. And charging price ranging from 3 to 40 cents per kilowatt hour, guaranteed threshold, which is the battery level you are promised by the end of the workday or departure, and override allowance, meaning how many times per month you can bypass the managed charging schedule, and a monthly cash reward for participating in these programs, a minimum threshold, that which managed charging won't active below this level. And the charging speed from 10 to 15 miles per hour. For directional charging on the right side, we have a similar structure, but adopted for vehicle to grid. Charging price goes higher, up to 60 cents per kilowatt hour. This is actually kind of California kind of, context. So we kept the guaranteed threshold. We added a monthly event occurrence, meaning how often your car would actually discharge energy. There is an event reward paid per vehicle to grid event and maximum discharge level, which caps how much energy can be pulled from your battery. So one important limitation here to note is this is a stated preference experiment, and so there may be hypothetical bias, what people say they'll do versus what they actually do in practice. So you have to keep that in mind. Going to the methodology section. Yeah, it's a kind of universal model that we have actually deployed, and we use the multinomial logic model, which I think most of you guys are familiar with it. I don't want to walk through it. We also use the we didn't fix the error term, so we use the kind of consider the normal kind of distribution for the error. Then we try to estimate that. And that's the only thing about it. So moving to the next third column. Okay. So first outcome, what actually matters to employees when deciding whether to enroll in this program? So we calculate the relative importance across showing how across we calculate the relative importance scores actually showing how much each attribute influence their decision. So let's start with managed charging. We found that the charging price dominates at 63%. Employees care most about what they are paying, right? But charging speed also goes second, and nearly 31% is interesting because conventional wisdom says slower level 1 chargers are fine for workplace charging since we have all day, but in managed charging content employees who want faster speed. Probably because they're giving up the control and when reassurance they'll get enough charge. The guarantee threshold comes in this next one. About 40% employees want to know they'll leave work with a decent battery level, and the minimum threshold and override matter less, around 9 to 10%. So now here what gets interesting. Look at the bidirectional, charging, the pie chart. So the charging price jumps to 63% important, and guarantee threshold takes the remaining 37%, and that's it. Everything else we tested that per event cash rewards and how often these charge event happen, the maximum discharge level, none of them were actually statistically significant. So what does this tell us? So we got the great employers, have much higher barriers to acceptance. Actually, they are, letting their car give energy back, which feels riskier. We have battery degradation kind of concern. So price becomes more critical. And battery guarantee is, surge in importance. So, next we then go to the last outcome. So we so far we know what matters, right? But employers, look at the employer side, they need like practical guidance. So if they cannot offer, free charging, as I said, what else they can do? This is how we basically, created this kind of sensitivity analysis after that. So we set a baseline scenario. Think of it like a middle of their road program. They're starting at 50% enrollment. Then we asked what change in attribute would produce the same like 5% boost in enrollment. For example, you look at like the baseline value for managed charging, 40%, 40 cents kilowatt per kilowatt hour for charging price, or without 0 events per month and 50 miles per hour charging speed with 60% battery guarantee threshold and 40% charge, 40% battery. That is actually brings you the 50% enrollment. So how we can boost that by 5%? It turns out there are like a multiple ways. For example, we can like reduce the charging price by 10 cents per kilowatt hour. It gives you the same result, but like increasing your charging speed by 5 miles per hour. So or increasing your guaranteed threshold battery by 9%. And there is a typo here. So because I'm just mentioning charging speed with the actually minimum battery threshold. So that's why I got confused. So similar to the charging, the bidirectional charging programs, increasing the cost by just 0.8 cents per kilowatt hour produce your same enrollment, 5% boost enrollment if you increase your guaranteed threshold by 5%. No, yeah, I think that's kind of messed up. Yeah.
Typo.
Yeah, that is a real typo, I think. I don't know.
That's fine. That's what we're doing.
Yeah. Anyways, so let's go to the conclusion. As I said, it could be practical for employers side. Maybe instead of like increasing or reducing the charging cost by a lot, they might lose the revenue. They can increase the other attributes, and they can still probably produce a similar results for the enrollment. Like for example, they can increase the guarantee threshold for those kind of things. So they can see like what are the trade-offs and which one works best for them. Thank you so much. That's why you're trying to prepare the table, at night.
Yeah. We got a month, so you're good.
Yeah.
3 weeks. I'm a little confused as to how you got. I might have zoned out for a second. Excuse me.
Yeah.
These 35.81%, 30.75%.
Oh yeah. So we calculated partial. The partial utility, right, for So we use the model, right? We get the coefficient, we can calculate the partial utility, marginal utility for each attribute.
Yep.
Then we apply to full all the responses, how much it can the average importance of that each utility for each attribute across the whole population.
So you have the coefficients, which are the marginal utilities,
Yeah.
and you just apply the model.
What do you mean by apply model?
I don't understand how you get 35 points. Like it's kind of hard to do this, to say which one matters the most without doing sensitivity analysis.
No, so no.
Could you like somehow standardize the input data?
I don't know. This one is kind of. Okay, I'm gonna just share my. I'm so sorry. I don't know why it's kind of lagging right now. So I cannot.
You need to zoom in.
I don't need it, right? Okay, so just like back to your question. Sorry.
Yeah. I'm just not sure what the calculation is, what the methodology is to get percentage impact based on a parameter.
So we have like so we use the MNL model, right? MXL model, right?
Yeah.
So we get the coefficient, right? But you agree that we can calculate the average part force utilities for each day.
The average what?
Average part for utilities.
Average
Part
partial
for
utility.
yeah. It can be calculated. I mean, if you're familiar with this kind of modeling, it's just commonly used for this kind of framework. You know, you usually. So that basically means, I mean, in simple language, that the marginal utility that each attribute provides, you know, and contributing to the outcome.
No, I know what a marginal utility is.
Okay, right?
What is this average partial utility?
So the average partial utility is gonna be so you use the model to get the predicted outcomes.
Sure.
And you can average out the part that you isolate the issue attribute and just get the average what that marginal utility is.
I'm not sure about that. Another reason that it feels quote unquote wrong is if you look at your next table, and you're trying to get this 5% point or 5% increase in someone joining the program.
Okay.
The first row of that table requires I think, 25% decrease in cost. And the third row only requires a 10% increase in charging speed. So you need a much bigger decrease in cost.
You're talking about the 5% equivalence value, right? Okay.
But your table says that cost is the most important. Your outcome one.
Well, so for managed charging, so I said so 10 cents decreasing 10 cents for kilowatt hour, right? 40, so that's like 25%.
Yeah.
So but consider this fact, we are holding other attributes constant.
Sure.
Right?
With exactly what you did for outcome one. You have everything else constant.
Yeah, but this time we're actually like predicting them or using prediction. For the importance is not about prediction actually. It's about how each attribute like influence the utility function, the marginal utility. How imagine you have a coefficient, you want how it's
So it's probably not scale dependent. So if I
No.
so if I put my dollars in cents, it would completely change the percentage impact.
No, if you put your no. So you're thinking about I think you're mixing up the average importance with the equivalency. So equivalency is just more practical. That's why you're trying to put dollars.
Well, I'm not saying that okay.
So the
This is not
average
an academic proof that the first part doesn't make sense if the second part is different, but it was just an indicator that something seems odd to me about that first outcome.
okay. But the average importance is just more about utility function. But utility function doesn't mean anything. Like 1 unit of utility, what does it mean for?
Well, that's my point.
So that's why we came to the equivalency value that's been more meaningful.
No, but I don't have any problem with the equivalency. It makes sense to me. My issue was the outcome one.
Yeah, so the outcome one was just more about I want to say that you got a bunch of coefficients, right? Different numbers, like 0.971, like minus something like that, right?
Yeah.
So you can say if the value of the coefficient is -2 and the other is -1, it doesn't double up or more.
Agreed.
Right? So, but you have to isolate that coefficient, right? To see how it changes the utility function. So that's how you can say that, what's that importance of that variable in utility function.
All right. Thank you. Sorry.
It's basically saying how it compared to the other attributes, how it can change the utility function.
I definitely see the value in being able to say which would be the quote unquote most impactful. I'm just yet to be convinced that
how it calculated
that anyone can do that.
Yeah, but if you're asking how it calculated, I mean, I cannot write it down right now, but there's definitely some kind of equation that can calculate that. I'm not the first one that came up with this idea.
Well, in my opinion, what is a bit counterintuitive is that if price is that important, right, in the marginal utility, right, but you have to decrease a lot the price to just gain this 5% compared to, right, we saw that the charging time is apparently not that important, but then
actually I'm trying to show the that's fine. So I don't know what happened. I can't even do anything. So I'm looking right now. So if you decrease the price by 10 cents per kilowatt hour, which is actually a lot.
Which is a lot, yeah.
Which is a lot, right? You can get the same results by just increasing guaranteed battery of 5%, like from 60 to 65.
Yeah.
So that you can see that how important that actually matters, If it's super important, that means that you have to change the utility a lot to get the same value compared to the other attributes.
Yeah, no, and I agree, but the first section, right, like the previous section was saying that price is actually more important than.
Well, yeah, that's one. So the price is important.
Do you not see the contradiction?
No, the average.
I'm not saying you're wrong, but it is contradictory.
The average importance is mostly about telling what you got from the model, right? Just to see that how the coefficient are matters the most. But you cannot say 10 cents because it's a lot, because what's the scale here? How you can compare that?
Yeah. Well, maybe I'm just I don't know.
Right, you cannot say 10 cents. I mean, actually, I was wrong. I was saying 25% decrease in 25% matching 31% importance in because we are not talking about the scales here, and the scale doesn't go through the model, right? You cannot say why 10 cents is just 25% less money for price changes, but what the importance was 31%. Right, so that's why we're trying to do sensation analysis to see how it actually would be the practice with working with real numbers. Real numbers doesn't mean anything in the model.
Yeah. Yeah, it was really good.
Yeah. Is it a binary model between two programs?
No, we are not comparing two programs. We just put them in the ones kind of.
Binary
two separated models.
enroll or not enroll.
Huh?
Binary choice between enroll or not enroll, right?
No, it's just when you have a set preference experiment, you're just showing two different scenarios, and there is no preference at the base at the ground, to see which one is better. You just ask them which one you choose with different.
How many alternatives did you show to once?
We showed three
alternatives, one scenario, and
three different scenarios.
is there any opt-outs that?
No, we didn't allow any alpha. Yeah,
These are forced, these forced to.
yeah, you have to get first. It basically assume that you already enrolled in this program. Yeah.